All right, folks, I'm going to go ahead and get started. It looks like pretty much everybody's done with the quiz. Looks like the numbers aren't changing at all, and we've pretty much got everybody with results in at this point. By the way, it looks like the quiz results look really good. You guys are getting this stuff down, so this is good stuff. I'm glad to see that everybody's really working through this. I feel like everything's becoming maybe just a little bit more understandable here lately, which is a good thing. All right, so I want to keep on going with calorimetry today. So what I really want to do today is to sort of compare and contrast the kind of calorimetry that we talked about on Friday, which was coffee cup calorimetry or simple calorimetry, and compare that to bomb calorimetry, which was the topic of the video for last night. So bomb calorimetry is considerably more complicated only because we're using a much more complicated apparatus of measurement. And we kind of talked about all the various parts of the bomb calorimeter in the video. But just a few differences before we move into some example problems. So if I'm just doing simple calorimetry, just to do a simple comparison here. That's your coffee cup calorimetry. If I wanted to get an expression for Q or heat that was transferred, for example, in a chemical reaction or between two substances that come into contact with each other in a simple calorimeter, we use the equation that you saw in the quiz. And that's equal to C, which is the specific heat of the material times the mass times the change in temperature. Okay, so remembering here that this lowercase c is the so-called specific heat. So if, for example, we had a substance that is absorbing heat, right, from its environment or from the surroundings, all right, the specific heat is giving us some measurement of how many joules it takes of heat absorbed to raise 1 gram of that substance by 1 degree Celsius. So we said it's a property of the substance. So remember, that's in terms of joules per gram degree C. Okay, so we can look up any substance like aluminum on the quiz, for example, and we can find a specific heat for that. All right. So we're kind of used to using that equation in the context of normal calorimetry or simple calorimetry. But now, if we're talking about bomb calorimetry, the equation changes just a little bit. So the issue we have when we're talking about bomb calorimetry is now the bomb and the calorimeter and the whole assembly is what's actually absorbing the heat. Okay, so remember what's going on here. We're going to have, for example, a combustion reaction inside the bomb. Okay, and we're going to set that combustion reaction off and it's going to give off heat. So it's an exothermic process. Now what's going to happen? Well, that heat's going to get absorbed by all the various components of the calorimeter. So the heat gets absorbed by the bomb, it gets absorbed by the water in the calorimeter assembly that's surrounding the bomb, it gets absorbed by the thermometer, the stirrer, the actual interior of the calorimeter assembly itself. The whole thing becomes a single absorber of heat, if you will. Okay, so in this case, I can't really assign a specific heat to a given substance like we can in the case of a simple calorimeter. For example, if the heat sink in a simple calorimeter is water, well, we just use the specific heat of water and Q equals Cm delta T. But in the case of a bomb calorimeter, water is only one component of the whole that's actually absorbing the heat. All that other stuff is absorbing too. And each component of the bomb is going to have its own specific heat associated with it. So what we do is we calculate a new specific heat, but it's for the whole bomb assembly, okay, the whole calorimeter assembly, because everything's absorbing the heat. So in this case, I'm going to use a big C, and I'm going to put CAL under it to show that it's essentially the specific heat of the whole calorimeter assembly, as opposed to just one part of it. And then we still have the delta T here. Okay, so notice the mass term isn't there anymore, okay? So that's kind of brought into C. So C now contains that mass component. And when we get right down to it, this is going, if I solve for it, let's just go ahead and do that. C cal is going to equal to Q divided by delta T. So what should the units on C cal be? Well, it's either going to be joules or kilojoules per degree Celsius. Okay, so your units are going to be some sort of heat unit per degree C. All right, so that's what we've got. Now, we're going to name this thing something else. We're going to call it actually the heat capacity of the calorimeter. Or sometimes we call it the calorimeter constant. All right. But essentially, that's what we're measuring. It's the specific heat of the whole calorimeter assembly. All right. So the deal is when we do bomb calorimetry, we kind of have to do it in 2 steps. We have to know what CCal is before I can actually use the bomb calorimeter to measure the heat of combustion of an unknown substance in an unknown reaction. So there's a calibration step we have to do before we do the analysis step. In other words, we have to do a separate experiment to get the calorimeter constant. Okay, so how would we go about doing that? Well, basically, to get CCal, I need 2 things. I need to know a Q, and I need to know a delta T. So obviously, delta T is something we can measure through a simple temperature difference using a thermometer. But what about the Q part? Well, here's how we do it. We're actually going to take a known combustion reaction, okay, that somebody measured separately in another calorimetry experiment, and we're going to use that to get Q, okay? In other words, if I know how much of that substance I burn, and I know its heat of combustion, then I can determine the total number of joules of heat that that reaction is giving off. And then all I have to do is measure the delta T associated with that, and that gives me the CCal. Okay, so I need to do the calibration step first, and then I need to follow that up with the actual analysis. So that's what we're going to do in the next 2 examples, so you can see exactly how that's done. Okay, so in other words, there's going to be some sort of a reference hydrocarbon we're going to use to calculate CCal. All right, one other thing I just want to share with you, and that is in many bomb calorimetry experiments, we don't really talk specifically about heat, even though that really is what we're measuring. We talk about heat in terms of something called enthalpy. And the next video actually talks more about enthalpy. So that's, next video you guys are going to look at. But basically, enthalpy and heat are used interchangeably in this course. But technically speaking, enthalpy is given as heat measured at constant external pressure. Now, normally in a calorimetry experiment, especially like a simple calorimetry experiment, the external pressure is just the atmospheric pressure bearing down on the system. Okay, so, that's normally taken to be a constant. So when we measure a heat under those constant pressure conditions, we can express that as an enthalpy. The two are exactly the same. Okay, they're both measured in joules or kilojoules, and we treat them exactly the same way. And by the way, enthalpy is actually given as a capital H, or oftentimes we see it as a delta H, because what we're really measuring here is a change in enthalpy associated with a system. But basically, we can say that heat and enthalpy are the same thing. So if you see enthalpy in the context of a calorimetry problem, for all practical purposes, what we're really measuring is heat. Okay, so I just wanted to make sure you guys were aware of that distinction, and more about that in the next video. All right, so let's actually, by the way, any questions at this point before I move on into the example? Anything not make sense? Okay, so we got that context in place now. So let's take a look at example number 1, which is going to actually deal with the calibration of a calorimeter. All right, so I've got a sample, and this sample is going to be some sort of a hydrocarbon. I don't tell you what it is. But when I burn it inside the calorimeter, it's going to give off 5,228 calories of heat. Okay, and then what I can do is measure the temperature change associated with the calorimeter assembly when that happens. And that temperature difference turns out to be 4.29 degrees Celsius. Okay, so again, I'm burning some hydrocarbon in my calorimeter, and I'm getting 5,228 calories of heat associated with that. Okay, now I've got a delta T that goes with that. So now what I want to do is calculate the heat capacity of the calorimeter in terms of kilojoules per degree Celsius. So this is just how we're going to do it. All right, so first thing I have to recognize is that I've got my equation, right? I know that the Q of the calorimeter, so now the calorimeter is my focus. I can think of the calorimeter as kind of like my system because it's really what I'm focusing on here, is going to equal to big C calorimeter times my delta T. Okay, that's the equation I just gave you above. Now I also know that I can say that minus Q, which is heat of reaction, I know that's negative because the reaction's giving off heat, right? It's an exothermic process, has to equal to Q for the calorimeter, right? And then that's going to equal to C cal times my delta T. And that's the delta T, again, I associate with the calorimeter assembly. All right, so now I'm kind of set up in a situation where I can get what I need just by simply solving for C cal. But before we do that, let's go ahead and just get calories converted over to kilojoules because I need heat in terms of kilojoules. Okay, so 5,228 calories of heat are what actually got measured. So let's convert those over, 4.184. And that's going to be joules per calorie. And that's a conversion from the first day that we talked about this stuff. And then I know that 1 kilojoule is what, 1,000 joules. Okay, so calories cancel with calories, joules with joules. I'm left with kilojoules. So I end up with 21.87 kilojoules of heat. Now notice that I'm leaving it as a positive value here because I'm couching it in terms of the heat that is absorbed from the reaction by the calorimeter assembly. So again, I'm focusing on the calorimeter assembly now as my system. Okay, so now what I can do is I can solve for C cal. So C cal turns out to be Q absorbed by the calorimeter, which is what I just calculated above, divided by my delta T. Okay, so my Q cal here turns out to be the 21.87 kilojoules of heat divided by the delta T given in the problem, 4.29 degrees Celsius. And I end up getting 5.10, I think that's correct sig fig wise, kilojoules per degrees C. Now again, something we have to recognize here, and that 5,228 calories, okay, that wasn't really a direct measurement that we made, okay? As it turns out, that's something we can actually go off and calculate, all right? And the way we do that, again, is because I know the mass of the standard hydrocarbon that I'm burning, how much of it I used, which I can convert to moles. And then I also can go look up for that hydrocarbon, the heat of combustion, okay, which is going to be in terms of, in this case, calories per mole or something like that. So if I know the moles and I know the calories per mole, I can calculate the number of calories. And again, that was based on somebody else's experiment, okay? So that's normally how we do this. All right, so that being the case, I've now got the calorimeter constant for the calorimeter. Okay, so again, this is based on burning a reference hydrocarbon whose heat of combustion I already know because somebody else did that experiment. Okay, any questions about that at this point? All right, so now we can go do something with it, right? So this is kind of part 2 of the bomb calorimetry experiment. So once I have the calorimeter constant, now I can actually use the calorimeter constant as a means of being able to determine a heat of reaction or enthalpy of reaction for an unknown species. All right, so we're now setting up a new bomb calorimetry experiment, okay? And presumably we know the C cal at this point because somebody went and measured it. All right, so in the second example, we've got a bomb calorimetry experiment. It's performed with xylose, which is a hydrocarbon. So it's C5H10O5 is its formula. That's the combustible substance. That's what we're burning in there. And the data that we're going to get is the following. I'm going to burn 1.183 grams of the xylose. So I'd have to weigh that out, right, well in advance before I put it in the bomb. My C cal for my calorimeter assembly, because presumably I've already gone and calibrated it, is 4.728 kilojoules per degree Celsius. So that would have been obtained from an experiment very similar to what I did in the prior example problem. So that's a piece of information now we have about our calorimeter assembly. And I can measure an initial and a final temperature. So the initial temperature of 23.29 degrees Celsius is the initial temperature before I set off the reaction. And T final of 27.19 degrees Celsius is the final temperature, or the thermal equilibrium temperature we get when the reaction has been set off, okay? So the main thing we normally want to do here in part A is to determine the actual heat or enthalpy of combustion of the xylose in kilojoules per mole, okay? And then we'll come back to B. So let's tackle A first, all right? So again, I can kind of go back to my original equation, where I can say that Q for the calorimeter, that's the heat absorbed by the calorimeter, is equal to the big C, that's my calorimeter constant or heat capacity of my calorimeter, times the delta T that the calorimeter assembly undergoes. Okay, so this is going to let me actually calculate a magnitude of heat. And I've got everything I need because I've got the C cal for my calorimeter and I've got a delta T. So that gets me to a magnitude of heat absorbed by the calorimeter. All right, so let's go ahead and just plug some numbers in here. So C cal is what, 4.728. And that's kilojoules per degree Celsius. And then you'll see that if I multiply that by the delta T, and I could go up and calculate my delta T upstairs, that turns out to be, I think I have it written, 3.90 degrees Celsius. You guys could check that for me if you wanted to. So I'm going to multiply by that. And you can see what's going to happen units wise. The degrees Celsius are going to cancel each other out, and that's going to leave me with a heat. So I'm going to end up with a heat in kilojoules because that's what my calorimeter constant is in terms of. And I end up with sig figs getting 18.4 kilojoules. Now keep in mind what that represents, guys. Again, I'm still looking at this from the point of view of the calorimeter being the system, right? So that 18.4 kilojoules of heat is positive because the calorimeter assembly absorbed it and the reaction gave it off, okay? But now what if I wanted to couch this heat back in terms of the reaction? Because that's really what I care about in this part of the experiment. How much heat's the reaction given off? Well, if I know how much heat got absorbed by the calorimeter, well, then I also know how much heat got evolved from the reaction. It has to be the same, right? So I can say that Q cal is equal to minus Q of reaction, right? So now, if I put this in terms of Q reaction, and I'll just do it this way, that's now going to equal to the negative of Q cal, so that's going to be minus 18.4 kilojoules of heat evolved. And that makes sense, right? Because we're now talking about the heat given off by the reaction instead of the heat being absorbed by the calorimeter assembly. Okay, so that's an exothermic process, and that's exactly what we'd expect to see from a combustion reaction. Everybody okay so far with what we've done? Okay, good. So I have another piece of information I've got to use because I'm supposed to actually express my heat of reaction in terms of kilojoules per mole. Now, what's the mole part? Well, that's the moles of xylose that I actually burned. Okay, and I can get out that because I think I have the mass of the xylose that I burned, and I have a chemical formula for it, so I can get a molar mass. Okay, so from those two things, I should be able to get the moles of the xylose burned. So let's go off to the side and get that. Okay, so I have 1.183 grams of the xylose, that's C5H10O5, right? So now I can go off to my periodic table and calculate a molar mass of that. In other words, the mass of 1 mole of xylose. Okay, so know that 1 mole of C5H10O5 corresponds to 150.13 grams of it. Okay, so grams of xylose cancel with grams of xylose, leaving me with moles of xylose. I get 7.880 to sig figs times 10 to the minus third. And that's moles of my C5H10O5. So that's actually the amount of xylose that got burned in the bomb, okay? So that's the mass that corresponded, or sorry, the number of moles that corresponded to the heat change I've got. So now I can express my Q reaction in terms of the correct units. I wanted kilojoules per mole, so I can do that now. So I've got minus 18.4 kilojoules divided by the number of moles of it I burned. And that turns out to be minus 2.34 to sig figs times 10 to the third, I believe, kilojoules per mole. All right. So what that gives me now is that nice piece of information about xylose. I've got its heat or enthalpy of reaction in terms of kilojoules per mole. So guess what I could do now? If I wanted to do another calorimetry experiment using some other species, I could now use xylose as my reference hydrocarbon because I now have its heat of reaction expressed in kilojoules per mole. Okay, so I could use it to basically calculate a C-cal for another calorimeter experiment if I wanted to do that. Okay. All right. So questions about part A at this point. All right. So let's just look back at part B, which is actually pretty simple. It says write the reaction equation for the combustion reaction and represent the delta H of the combustion process for that reaction equation. So this is just going back and making sure we know how to write a combustion reaction. All right, and balance it. So remember, in any combustion reaction, we're talking about burning the hydrocarbon. So what does burning it mean? It means combining it with oxygen and applying a spark, right? So we talked about combustion reactions before. I think back when we were balancing reaction equations. So C5H10O5. So oxygen, and that turns out to be, I believe, a solid. Normally, these hydrocarbons are solids that we weigh out and we actually compress into a little plug when we put it down in the bomb there. And we end up with O2 being the reactant. Remember, that's in large excess. Not that the question asks us about that. And I'm going to make, what two products do we always get in a combustion reaction? Anybody remember? Anybody remember one of them?
Water.
Water, yep, sure thing.
CO2.
Yep, you got it. So we would get water vapor and carbon dioxide. Good. Okay, so then you go back and basically get this thing balanced. And when you balance it, it turns out that you need 5 O2s, you need 5 waters, and 5 CO2s. And you guys can go back and verify that it's correctly balanced. Okay, it's not a redox. You can just do it by inspection. All right, so now, how would I actually express my Q of reaction here that I just circled up here? Well, the way we do it is we actually reference it back to the actual hydrocarbon here. Okay, so I would express this exactly as I calculated it as minus 2.34 times 10 to the third kilojoules per mole of the hydrocarbon that I burned. So I'll write that as moles of C5H10O5. Okay, so that's how I would express it. It's always expressed in terms of the moles of the hydrocarbon that I burn. But it's interesting to keep in mind that for every mole of hydrocarbon that I burn, I don't necessarily make 1 mole of water or 1 mole of CO2. Okay, those things can actually vary based upon balancing of the chemical reaction equation. So in this case, for every mole of hydrocarbon that I burn, I'm making 5 moles of water molecules and 5 moles of carbon dioxide molecules. But we always end up referencing everything back to the hydrocarbon. Okay. All right, folks, any questions about that? I mean, that kind of takes you through the whole process of how bomb calorimetry calculations work. Everybody good? All right, so I'm going to run you back to Chem 101. So we actually have a little bit of calorimetry practice we can do. I looked at it a little earlier, and I believe one of the questions goes back to looking at a simple calorimeter problem, like coffee cup. And then the second one involves a bomb calorimeter. So they're actually not very hard problems to do. And I think I gave you way more time to do them than you're really going to need. But let's go ahead and start. Okay. You can have a look at the problems. Here they are. Okay. So the first one looks like a simple calorimetry problem like we did on Friday. And the second one looks like a bomb calorimetry problem. And take a look at number one. They're asking you for a delta H in kilojoules per mole. That's an enthalpy of reaction. Okay, but we know what that is. It's really just a heat measured at constant pressure. So we can use the two interchangeably. Kind of get a mixed bag of answers there on number one so far. One thing as I look at it is watch your signs. Watch your signs. ask yourself, is the process in number one endothermic or exothermic based on the information you're getting?
Excuse me.
Sure,
Could you go over how we do question 2?
sure. Yeah, we're going to use our regular calorimetry stuff here. Okay, so let's look at number 2. See what we got. All right, so I know I've got 0.0 0.0801 moles of my compound, right? That's what's being burned in the calorimeter. And I know what my delta T is. My delta T turns out to be, and they give you that, 2.19 degrees Celsius, right? All right. I also know the C-cal. They give me that as well. That's the calorimeter constant, or the heat capacity of the bomb calorimeter. That's 1.229 kilojoules per degree Celsius. All right, and I want to know the heat of combustion of the hydrocarbon in kilojoules per mole. So I got everything I need. Okay, so the first part I'm going to use to get my Q. Okay, so my Q in terms of my calorimeter is going to be equal to C-cal times my delta T. So my C-cal is 1.229 kilojoules per degree Celsius. I'm going to multiply that by my delta T, which is 2.19 degrees C. Okay. And I got my calculator here. I can actually figure it out. And to sake figs, I get 2.69 kilojoules. Now that's for the calorimeter. That's what the calorimeter actually absorbed. Now, if I want my Q of my reaction, remember what I have to do. I have to change the sign on that because the reaction's actually giving off the heat. So I'm just going to make it negative, 2.69 kilojoules of heat now being given off by the reaction. So now I want my Q in terms of kilojoules per mole. So what do I have to do? I have to take this and divide by the number of moles of compound that I burned. So that's 0.0801 moles of compound. And they wanted kilojoules per mole, right? So it looks like that's the right thing. So divide by 0.0801, and I end up getting, looks like minus 33.6 kilojoules per mole. Does that make sense?
Yes.
Okay, good. Yeah, looks like that's what they got. So it looks like we did it right. All right, so you have a few more minutes to work on this if you guys want to. Any other questions before I sign out? Anything else you guys want to know? All right, so as far as Wednesday goes, make sure you're looking at the next video, which I think is the enthalpy video. And again, be prepared for a 5 for 5 quiz. So be looking at stuff we did today, and anything in the enthalpy video is also fair game. All right, it's a beautiful day out there, guys. So get out there and enjoy it. If there's no other questions, I will see you guys on Wednesday then.